thanks everyone for being here. I feel inspired by Steve's caveat yesterday to inform you that if you see me hobbling around on these while I'm here, it was not from any fun St. Paddy's Day shenanigans. It was from an unfortunate incident where I was simply trying to exercise, and that was my first mistake. So yeah, just sprained ankle fun. So thank you again to the committee for inviting me to hear more about the work that we're doing at Cornell in collaboration with many partners, in particular members of USGS. So just to give a brief background, active acoustics is a remote sensing method that allows large areas of the water column to be sampled very quickly. You may be more familiar with this method than the usual people, having seen several talks on acoustics before and later, but you may also be more familiar with this method described as sonar. It's essentially that active two-way direction of sound where we ping high frequency, it reflects off of targets in the water, and we read that energy back. And we can call that reflected sound backscatter. It's energy, and we'll to define a few terms I'll use through this presentation. SV is volumetric backscatter, so you'll see that. That's the little color blobs you often see in echograms, is how we represent that. It's a logarithmic measure. I'll often mention NASC. NASC is just a scaled linear measure of that backscatter energy. And the most important thing for all of you to understand is that NASC is proportional to biomass, so we often use it as a proxy for biomass. So if you imagine this ship moving across a transect, you get something that we call an echogram. These are those color blob images that you've seen previously at times. Basically you can see the ship moving over the water. Areas that are red are high density or a high scattering source, such as the ground. That's that strong line at the bottom is the sea floor or the lake floor. And the little specks through the water, the little red specks through the water, are fish in the water column. So here the y-axis is depth and the horizontal x-axis is distance. So the goal of this project is to look at potential sources of biases done in these long-running, we saw from Dave this morning in the Michigan session. This has been done for many, many years via vessels. It's a very useful method to estimate fish populations. However, that does introduce potential sources of bias that we want to make sure we're accounting for. We want to see how much of a problem they are, and that is the main goal of the project that I am currently on. So I'm going to talk about a couple of those projects today that we have been investigating these potential sources of bias. The first is potential vessel avoidance. Ships are very large and very loud, and there is some evidence, particularly in marine systems. If you were here yesterday, you saw Tom give a talk on this, where the entire density of water, of fish in the water column move as a ship approaches. So this is from a stationary source that tracked fish as a ship approached, which is that line, and you can see the entire movement of fish in the water column. So you could see how that could potentially bias if what the ship is seeing is only right here. So that's one thing to look at. The second source I'm presenting on today of potential bias is something we call the surface acoustic dead zone or acoustic blind zone. This is where in the area just below where just below the surface, we potentially miss fish. This is due to a couple of reasons. Potentially, if we have a down-looking echo sounder that's attached to either a ship hull or a pole mount off of the ship, or off of a keel in the case of a drone. And that's some distance in the water, which means you, by definition, can't see any fish sitting higher in the water than that down-facing source of sound. That orange thing being the transducer and the source of sound. The other potential reason is that within a certain distance of the transducer, we don't use the sound there. We have to exclude that. Sound behaves a little bit differently. The beam hasn't fully formed. So what that comes down to is there's a few meters near the surface, something in the realm of, in the ships we use in Lake Superior, 3 to 5 meters that could potentially have to be chopped off. And then that's even without considering the possibility of lots of air being entrained, so bubbles entraining down from interaction of waves with the hull. So it could be even lower than that. So what we want to see is there potential bias due to these two sources? We used two different autonomous vehicles in this study. This is in particular in Lake Superior in 2022 in the Western Arm. There's increasing interest in autonomous vehicles. It could be cheaper to operate than crewed vessels due to fewer crew being active at one time, cost of fuel, and et cetera. Also potential increased spatiotemporal coverage, where those autonomous vehicles can be out when ships can't, and they're quieter than ships, generally speaking, so we can get an improved signal-to-noise ratio. Once again, I'm talking about these drones moving in the western arm of Lake Superior in 2022. In this summer, so this is August into very early September, we had two sail drones. These are these two different paths, the orange and the blue dotted lines, as well as so this is a surface vehicle, as well as an autonomous subsurface vehicle, long-range AUV, which covered in a certain same set of transects, which I'll talk more about in just a moment. First, just to cover the sail drone, that again, it's a surface vehicle. It's entirely solar and wind powered, which means it's very, very quiet. It collects both acoustic and environmental data at the lake surface, which is great because that means we're getting environmental data at the lake surface as this is moving around all over the lake. The second is this subsurface vehicle, the Triton Long-Range AUV, or LRAUV. We worked with Monterey Bay Aquarium Research Institute to operate this vehicle in 2022 in Lake Superior. And it has both up and down looking echo sounders, which means it's moving through the middle of the water column and it's looking both up and down. So we're still seeing the whole water column, just from a different perspective. Also, this vehicle has to surface every few hours in order to communicate with the satellite. And so when it does, it's also actively collecting environmental data, which means it's collecting temperature profile data every few hours, which is great. That means we get co-located environmental data, temperature profile data, therefore habitat data with our fish density measurements. This is what an echogram looks like from that different perspective, where that black line is where the AUV is moving through the water column, and then the data above it are from the up-looking, and the data below it are from the down-looking echo sounder. Okay, so I'm going to go into the two studies of results I'm going to talk about a little bit here. This first study, it looks at how fish respond as a vessel overtakes the uncrewed surface vehicle. That's that sail drone. If you saw Tom's talk yesterday, this is a study led by Tom Evans in our group, but I'm going to cover a little bit of what was done in Superior to this particular overtake study. So this overtake design happened where the sail drone is moving along this path, one of the transects. The sail drone moves much more slowly than a ship. So at night, sail drone moves along in a straight path, and the ship kind of has to circle a little bit, and then once the sail drone has moved that distance, then the ship follows so that it's within an hour or two covering the same track. But coming up behind the sail drone so that, of course, it's not imposing on anything that the sail drone is actively seeing. This lets us do two different analyses. Both we can compare those 2 kilometer-long samples of the same path traveled by these two different platforms within 1 or 2 hours of each other, and also lets us look at the sail drone data as the ship approaches and see if we can see any changes in behavior detectable at the sail drone itself. Just to review a couple of differences that was looked at when we say differences between the sail drone and the ship. First was looking at this acoustic backscatter, again represented as NASC, which is the logarithmic, or the linear versus SA, which is the logarithmic. And we're looking at relative differences between these two. So this is sail drone minus ship. Another variable is looking at target strength, and this is important to think about. Target strength is the energy backscattered from a single source, which means that if we have a type of transducer or a type of echo sounder that lets us get detections from single in situ targets, we can get an idea of the backscatter, which is related to size of the fish, and get an estimate of what those targets are doing, where they are in the water column, and whether or not there's any difference between what the sail drone and the ship is seeing. And again, the last is target depth, because we can get exact target size, and single echo detections is what that's often called. We can look at both how big they are and where they are in the water. So we analyzed these results from 5 different vessels between 4 different depth layers. These are 20-meter height depth bins. Looking across the depths and of the variables tested, we found differences in the SA and TS, but not necessarily density when it came to statistically significant differences. However, it was marginal, and just to zoom in a little bit, when you look, you can see how each of these lines is a little bit to the right. Again, this is sail drone minus ship, and so that means it's biased a little bit towards the sail drone across these different depth bins. So essentially what this is telling us is we weren't seeing that massive difference that you saw in that echogram I showed you of the marine, all the fish moving, but you are seeing some amount of difference. That difference was not visible in any change in the sail drone as the ship approached. So we interpret that to mean that any differences, this minor difference that we are seeing, is right at the ship. So it's highly, highly localized to the ship. This second study I'm presenting on today, some preliminary results looking at examining that second potential source of bias in the surface acoustic dead zone. And this is by comparing the long-range AUV, both data within itself and comparing to the other 2 platforms, sail drone data and ship data. So we had these 7 transects. Here's a kind of closer look at them, and you can see these the 3 platforms, the time at which they were surveying, overlaid across these seven different areas. You can see that they are covered wholly or partially by our 3 platforms, so that's something to keep in mind. And as we're looking at this, I've pulled just the transects where we do have some of these same areas and distances covered. But we did have it covered by all 7 of these transects or locations covered by these 3 platforms, which is a great chance for us to look and see what these different platforms are looking at. So first, looking at just within the LRAUV data, what's seen by that subsurface platform, and looking at, this is in terms of NASC, so again, this is proportional to biomass, which can be useful to think about, especially because these are prey fish species, so we can think about it as energy in the water available for some of those larger predator species. If we're looking at the entire water column on first pass at this, it's not super impressive. So this is proportion. You can look at the orange is the proportion in the top 5 meters. This is just exercising that cutoff and looking to see what's there and what isn't. However, one thing to think about is that when we cut this off at the epilimnion, so that topmost layer, so these are depth habitats ordered by depth. And when I cut that off based on those profile data, I was finding massive amounts in terms of proportion of the biomass we were looking at are in those top 5 meters. And there's a reason this is so extreme, which our last talk may have clued you in on a little bit. So again, we got those profiles data from the LRAUV. And because of the uniqueness of 2022 as a year, how cold the water was and how high the thermocline was in some of these areas, starting, the upper metalimnion is within the 5 meter range, especially in the area, the Sand Island area, which is just west of Sand Island was that transect. And so because of that, this is where we're finding mostly rainbow smelt and the Cisco, particularly those young of year Cisco. And so this bumper age crop really contributed to that. And then just to get a better look at that and exactly what fish community is there. Each of these are 5 meter depth bins, and these are the target strength of those single echo detections of fish. And so you can think of this as when you see a peak that's kind of towards the left end of the x-axis, those are target strengths that are consistent with young of year. So because of that, and what you can really see jumps out is in that top 5 meters, it is very much those young of year fish, or sizes consistent with young of year fish, that we are seeing in those top 5 meters. Which then explains partially when we move this into density and do density estimates of the numbers of fish, why we're getting such high densities in that top 5 meters, particularly right around that red line being the 5 meter mark. So this is something really interesting and is an example that just by happenstance shows just how important looking at those top 5 meters can be in a year like this that's very cold and has pushed that epilimnion up very, very compressed into very tight near surface space. So yeah, let's again highest densities in kind of those top 2 5-meter bins. Looking at that, so moving from the LRAUV to looking at the Chi and the sail drone values, what should really jump out here is that we are seeing those highest density estimates. Again, this is by a 5-meter height bin for all platforms closer to the surface. And just to zoom in on that concept, and also in particular that in the Chi and the sail drone, we don't get any values above 5 meters because of that surface acoustic blind zone, which is exactly what we're looking at. To compare that a little bit better side by side, as that last plot is a little hard to see side by side, we can look at these. This is plotted in a log scale on the Y, so that's why it's enhanced a little bit. And in particular, that jumps right out where we can see we're getting density estimates from the LRAUV that we are not getting from the other 2 platforms. So again, those are preliminary results as we're continuing to look at these and look at the potential differences and why those differences are happening in terms of those density assessments. But it's clear even from what we've seen so far and what I've shown you already is that these 2 autonomous vehicles give us new perspective, new information. We've seen support for sail drone showing a little bit of bias in the ship density estimates, and we can really get an idea of, in situations where we have a large year class of yearling fish that are, or young of year fish that are right up in that near surface zone, could be really useful. This technology could be really useful if you're starting to get estimates for those fish communities. There are also large things to think about in terms of potential savings on cost, but especially in terms of reduced emissions. We're not using as much fuel. These are a lot of wind and solar powered, and then battery and buoyancy powered vehicles. I would like to acknowledge all of the partners on this project across USGS, Fish and Wildlife, Travel Nations, and more. With a lot of moving parts and a lot of people helping out on these projects. And with that, I will take any questions. I think I have a little bit of time.